Okay, let's get started, please. So we finished up with this thing last time, which was graphing polynomials, right? So graphing polynomials, right? And we were able to do something that was kind of cool, which was to get a pretty good approximation. So like, approximating the behavior near roots, near the zeros of the polynomial. You guys remember that? We had this thing. And there was this kind of complicated rule. Let me just say that this business that we did at the end of class last time of approximating behavior near roots is actually really simple if you think about it. It's basically just one sort of obvious idea. So here's the obvious, I think, probably intuitively obvious idea. Intuitively obvious idea behind that method. And it's just this, that, you know, if near some point, you know, A is roughly some value and B is roughly some value, then their product is going to be roughly the product of those values. Right. This is all that's going on in that method. Okay. So like if I say you've got these two things and you don't know what they are. There's A and B, right? There's A and B, and A is roughly 5 and B is roughly, you know, 7. Then the product is going to be roughly 35. Right? That you believe that, right? Right. So that's all that's going on with this. That's all that's going on with this method. Let me do an example just to make it clear how simple this is. So if you have a polynomial, this is kind of what we were doing. This is what we were doing at the end of the class last time. You have a polynomial like this. So here's your polynomial: x minus 1 squared times x plus 4 times x minus 3. Right? And where are the roots? Where are the zeros? Somebody just read them off. 1, -4, 4, and 3. Okay. And so we want to know about a behavior near the roots, right? So near those roots. So let's look at near 1. And all we do is we take the polynomial and we say, well, look, you've got x minus 1 squared, x plus 4, and x minus 3. And so we say, well, look, you know, this x plus 4, near 1, x plus 4 is basically going to be 5, right? Right? Near x equals 1, right? When x is basically 1, then, you know, this is going to be 5. This is going to be basically 5, and this is going to be basically -2, right? And so what's the polynomial going to act like? The polynomial is going to act like -10 times x minus 1 squared. Okay. Now, people always ask, shouldn't you plug the 1 into this one too? Right? If we plug the 1 into this one, we'd say, oh yeah, this is going to be basically 0, and so the product is going to be 0. Right? We knew that already. It's a 0, right? We don't want to do that because that doesn't give us any new information. Right? What we're trying to figure out, what we're trying to see is like, what does the polynomial behave like nearby? We're not interested in the value. We're interested in the behavior. Okay. If we wanted the value, we can just plug it in. Okay. But if we're thinking about the behavior, what it makes sense to do is say, well, look, these guys are basically -10, and so we've got this thing -10 times x minus 1 squared. Okay. So that's the idea. You basically, you know, look at the guys that are not that don't describe the root itself. Okay, so if we're at -4, right, then we would leave this guy and then think about the values of these things, right? So -4, here we get -5 squared, so let me just rewrite the order. Right, so this thing would be, basically -5 squared. This thing would be -7, right? So you get 7 times times 25, that's 175. So -175 times x plus 4. Right, and so on and so forth. Okay, and so this would, let's just do the last one. Let's do the whole thing. When x is basically 3, you would get, you're going to get 3 minus 1 squared, that's 4. You would get 3 plus 4, that's 7. So you get 28 x minus 3 times x minus 3, right? So that's what the polynomial is going to behave like near there, right? And then you would use those facts to graph your polynomial. You'd say, okay, well, we've got 1, -4, 1, -4, and 3, and we know that, right, near -4, this is going to look like this is going to look like -175, so it's going to be very steeply sloped downwards, right? Right, at 3 it's got 28, so it's pretty steeply sloped upwards, but not nearly as steeply as this one. I should make this one even steeper, right? And then at at 1, we've got a downwards parabola, right? -10, so we know it's downwards, and it's this parabola, it's this parabola, right? So we've got the parabola that's kind of like this, and we know that the polynomials are going to look like this. Okay, so this is what we're doing at the end of class time, and the idea is simple. It's basically, if this is basically 5 and this is basically -2, then this product is -10 times this. Okay, so that's all that's going on with that method. Okay, is it clear? Questions? Yeah. Okay. So what we're going to do today is finish up the chapter. We're going to basically do the same thing with rational functions. Okay, what we just did with polynomials, we'll do exactly the same thing with rational functions. And it's going to be, basically completely identical. So it's not that exciting. Let's just get through it, and then we can get, in the next chapter, we'll get to finally so-called transcendental functions. So 4.7, rational functions. So let's just recall the definition, right? Somebody tell me what a rational function is. Anybody remember? What's a rational function? It has the word ratio in it. It's a ratio of two things. Those things are... Anybody know? Are you just being shy, or you actually don't know? So rational numbers, right? You have these simple things, integers, right? And then you go to rational numbers, right? Rational numbers, which are ratios of integers, right? Like P, Q in the rationals, right? And the rational numbers are just ratios of integers. Same thing. The analogy is perfect here. It's exact here. We've got polynomials, and then we've got rational functions, which are just ratios of polynomials. Okay. So any function, a function, which can be expressed as a ratio. let's say, quotient, but really it's a ratio of polynomials is called a rational function. Okay. Often one makes another definition of proper and improper. So just like you've got proper fractions and improper fractions, maybe you can guess what do you think a proper rational function would be? Guys, guess you know what a proper fraction is, right? What's a proper fraction? Yeah, Amy. Right, the numerator has to be smaller than the denominator, right? So you have something like 4 over 5, right? Whereas 5 over 4 would be an improper fraction, or 4 over 4 would also be an improper fraction, right? Okay. Okay. So can you guess? Anybody want to make a guess? I'll give you 10 seconds. Yeah, Aaron.
With the degree on the top of the small.
Exactly. You want the degree of the numerator to be smaller than the degree of the denominator. Right. Right. And then improper would be the numerator is greater than or equal to greater than the denominator. Okay. So yeah, and if the numerator is bigger than the denominator, bigger than or equal to the denominator, you can actually do some division, and then change it into a polynomial plus a proper fraction, plus a proper rational function. You don't have to know this, but let me just show you something like that for fun. Okay, somebody give me a polynomial. Nope. Nobody wants to. X squared plus 3x plus 1. And then let's take something that's got a bigger degree, x cubed. X cubed plus 1, say. Okay. Right. So that's an improper. You don't have to know this, but it's actually kind of a handy trick. So you can actually do long division with polynomials like you do long division with numbers. Okay. So you don't have to know this, but this is actually might come in useful to you. So the way you simplify this is you just do long division. So you say, okay, I'm going to do x squared plus 3x plus 1 here, and then you do just run through your division like you would with numbers. You say, okay. I need to get an x cubed here, so I need an x here, right? And then you multiply, you get x cubed plus 3x squared plus x, right? You subtract, you get negative 3x squared minus x plus 1, and then you say, okay, I need negative 3x squared, so I'm going to subtract 3 here, right? And I subtract off negative 3x squared minus 9x minus 3, and then you subtract there, you get 8x plus 2, right? And that's your remainder. And so what this thing turns out to be is x minus 3 plus 8x plus 2 over x squared plus 3x plus 1. Okay, so this is how you would convert an improper fraction into a polynomial plus a proper fraction. Okay. Have I made a mistake, Jane? No?
No.
Okay. Just trying to follow. So this is just like, so like if you have 5/4, right, you could write this as, well, you got 1, and then you subtract off, right, and then you get, you know, remainder of 1. So this is 1 and 1/4. Right? That's all we're doing, actually. Right? Just exactly the same thing. You've got this thing, you're like, okay, you know, how do I divide it? And you get this factor, and then you get this remainder. It's exactly the same thing. Okay. So, in any case, what we're going to be so notice that remark, we'll deal only with rational functions. I think we'll only deal with rational functions where the degree of the top is less than or equal to the degree of the bottom. Okay, and where P and Q have no common factors. Right, so if they have common factors, right? If they had common factors, you would just cancel them out, right? Suppose you had something like this, you know, like suppose you had a rational function like this, you're just going to cancel out the common factors anyway. So it doesn't, you know, doesn't really make that much sense to include them. Okay, so we assume that they have no common factors, and you know, if the degree of the top were bigger than the degree of the bottom, you can just divide out and break it into a polynomial plus a rational function anyway. So it makes sense. You know, to me it would make sense to deal only with improper guys, because you can break it into a polynomial plus an improper fraction. But anyway, the book says we're going to deal with guys like this. Okay, so so that's just so that we don't have to do this long division all the time, I guess. So everything we'll have already gone through this long division process, and the common factors cancel out. But in general, you might have to do that yourself. Okay, so here's the simplest rational function. That's not a polynomial. Simplest, not a polynomial. Right, because polynomials technically are rational functions, right? It's the polynomial over 1, right? Which is also a polynomial. But anyway, the simplest non-trivial rational function is going to be 1 over x. Right? There's a polynomial on top, there's a polynomial on the bottom. Right, let's see about this polynomial. P of x is 1 over x. Let's think about this guy. Like, what does it look like? Well, at time 1, what's the value? 1. Thank you. At time 2? What? 1/2, thank you. At time 3? 1/3, 1/4, 1/5, right? So, right. What about at time 1/2? 2, right? So at time 1/2, it's 2. At time 1/3, so at 1/2, it's 2. At 1/3, it's 3. At 1/4, it's 4, and so on and so forth, right? Right. Okay. So, right. So here we've got these points. Right. This is 1, 1. This is 1, 1. I'm sorry. This is 2, 1/2, 3, 1/3, 4, 1/4, and so on and so forth. Right. And here we've got things like 1/2, 1, 1/3, 1/2, 2, 1/3, 3, 1/4, 4, and so on and so forth. Right. What do you guys notice about these numbers? Do you notice anything about the graph so far? Well, actually, let me put that off for a second. What do you notice about the symmetry of this thing? If I look at the graph y equals 1 over x, what kind of symmetry does it have? Symmetry about the y equals x. Symmetry about the y equals x line. Well, I guess I was more asking about like the replace x by negative x, replace y by negative y, that sort of thing. Is it symmetric? Is it symmetric about the right? If I replace x by negative x, do I get the same thing? Right. You got y equals 1 over x. Suppose you replace x by negative x. Well, you're going to get y equals 1 over negative x. Is that the same thing? No. Right? What if you replace y by negative y? You get negative y equals 1 over x. Is that the same thing? No. What if you replace both x by negative y and y, and x by negative x and y by negative y? Well, you get negative y equals 1 over negative x. Is that the same thing? Is that the same graph as this? Are these the same equations? Yes, right? Yes. Because the negatives will, you can multiply both sides by -1, and you get the same thing. Right? So what do you see? It's symmetric about the origin, right? So that is, if you flipped it over this way and this way, you should get the same thing. Right? So the graph is symmetric about the origin, right? And Vivi, you notice that in fact this graph is also symmetric about the line y equals x. Right? That's what I was trying to point out here, right? That 4 goes to 1/4, 1/4 goes to 4. Right? Right? 3 goes to 1/3, 1/3 goes to 3, and so on and so forth. Right? What does it tell you if a graph is symmetric about that line? It's kind of a review here. Talk to a neighbor. We have this graph, and the reflection about the line y equals x is the same graph. Talk to a neighbor for about a minute or so. I'm gonna walk outside. Anybody figure it out? Yes? No? Anybody want to say anything? If you take a graph and reflect it about the line y equals x, what do you get? you get the inverse function, right? The graph of the inverse function. So here we have a function, and we reflect it, and we get exactly the same function. What does that tell you? That the inverse function is the same as the function, right? This function is its own inverse, right? Which you would guess, right? Because if you take 1 over x and you feed that into 1 over x, you take the reciprocal and then take the reciprocal again, you return back to the original function, the original value, right? So yeah, this function is its own inverse, right? If I take p of x, right, that's going to be 1 over p of x. But p of x is 1 over x, so I get 1 over x, which is just x, right? So this graph is its own, this function is its own inverse. Okay, so just understanding this one function, 1 over x. So other observations. One, it's discontinuous. It's discontinuous. Right? It actually has this break here, right? Where it goes down this way. Yeah, it doesn't. In fact, it doesn't even have a value at x equals 0. Right. So it's discontinuous at x equals 0. Another thing you notice is that as x goes off towards infinity, what happens to the values?
They get closer to 0.
P of x tends towards 0, and as x tends towards 0 from the right-hand side, if x tends towards 0 from the right-hand side, then what happens?
It trends towards infinity.
Yeah, P of x goes upwards towards infinity, right? And as x goes to 0 from the left-hand side, P of x goes down to negative infinity, right? Right? As x goes to positive infinity, or x goes to negative infinity, right? The value tends towards 0. Okay, and you've probably heard these terms before. What one says is that the line y equals 0 is a horizontal, what's called a horizontal asymptote. Okay, all that means is that that the function becomes basically that line as you head off in that direction. Okay. So there's a lot of this basically like this, or roughly like this, that's going to happen right now. Okay, you know, my PhD advisor would say, morally speaking, the function becomes 0. You know, that's how he reasoned in his mathematics. He'd be like, well, morally speaking, these functions behave like something like this, and that's actually a really smart way of thinking about mathematics. Right? You want to have some sort of rough idea of how things behave. Okay, develop an intuition about things. Right? So like, yeah, it's basically 0. It's basically 0. And then, it's not exactly 0. You keep that in mind, but basically it's 0. Right? Just like those numbers were basically 5 and negative 2. Okay, so here, we've got these asymptotes. Right, as you head off in this direction, the function basically becomes the line y equals 0. As you head off in this direction, the function basically becomes y equals 0. As you head close to 0, the function basically becomes the line x equals 0. Right. So x equals 0 is what's called a vertical asymptote. But roughly speaking, asymptote just means that a line that the graph basically becomes as as x does something. Like as x goes off in this direction, as x goes to infinity, or as x gets close to this thing, or whatever. Okay. Let me just say that some people, when I, often students say, oh, the function is not allowed to touch that line. Like you're not allowed to touch the asymptote. It's okay. It's already actually okay to touch the asymptote. So if you have a function that goes like this, like, right, and then as time goes on, that oscillation decreases, and you head off. This function's horizontal asymptote would be y equals 0. It's okay. It touches the line millions of times, infinitely many times. It's okay. Yeah, there's some sort of taboos that people come in, like, oh, you're not allowed, the function's not allowed to touch the asymptote, but it's actually, there's no such taboo. Yeah, or like putting a square root on the bottom. Like sometimes you have students that are like, you're not allowed to put a square root on the bottom, and I'm not really sure what will happen, like what they think is going to happen. But it's okay to have a square root on the bottom of the function. There's nothing wrong with that. Okay. Okay. Let's see. Okay. So just like when we were talking about polynomials, we looked at monomials, right? Even monomials and odd monomials, right? And we said that these guys, basically behave like, behave like x squared. These guys behave, basically, oops, not x1. Sorry. Behave, the graphs look kind of like, a cubic, et cetera, et cetera. We'll make a similar comment about rational functions. So if you have something like this, 1 over x squared, 1 over x to the 4th, et cetera, it looks something like this. And then for the odd guys, 1 over x cubed, 1 over x to the 5th, et cetera. It looks basically kind of like 1 over x. So just to give you some rough sense of those guys. So these are the even guys, and these are the odd guys. Okay. So it. Okay, so let me just make. Sorry, I probably should have included this earlier. Comments on asymptotes. You have some function, some rational function, p of x over q of x. Okay. So vertical asymptotes. You just check where the denominator equals 0. And then for horizontal asymptotes, you check behavior as x goes to plus or minus infinity. Let me let me give you some example. So some examples. So first, let's say r of x is 4x plus 3 over x squared plus 3. Okay. So if you see something like this, you would say, okay, you know, where does it have? Does this thing have? Does it have any vertical asymptotes? So it'll have vertical asymptotes if wherever the denominator is 0. But this denominator never gets to 0, right? Because you see it's got x squared plus 3, right? So it has no zeros. You can't get 0 out of that, right? Because the x squared is always 0 or above, right? So it has no horizontal asymptotes. I'm sorry, no vertical asymptotes. Okay. And then for horizontal asymptotes, you want to look at what happens as x goes to infinity. Can people get sort of intuitively understand what happens as x goes to infinity? What do you think about this? 4x plus 3 over x squared plus 3. As x goes to infinity, anybody have some sense of this? Yeah, Stella.
Wouldn't it be something like, you know, you get like, say if you put like positive infinity, it would be something like infinity on top and then divided by infinity squared, which would just be like a fraction.
Which would be what?
Like a fraction.
Something like that. So you've got this infinity, something that becomes infinite on top, and you've got infinity squared on the bottom. Yeah. So actually, that infinity squared is going to be is going to dominate. Is going to actually beat the infinity on the top, and then it'll actually become 0. It'll be like 1 over. You can't really do this, but it's like you cancel off one of the infinities. So you get 1 over the infinity on the bottom, and so that'd be like 0. Okay. So yeah, the way you want to, you know, there are a couple ways to think about something like this. Let me move over to the side because I think people are being blocked by the camera. A couple ways to think about this. You think one way is that if x is really big, then these 3's don't matter, right? If you've got if x is like a quadrillion, and then you've got 4 quadrillion plus 3, and you've got a quadrillion squared plus 3 on the bottom, those 3's don't matter, right? So this is, morally speaking, right? It's going to be 4x over x squared for x large. Right? And that's, that 4x over x squared is just 4 over x, right? And then for x large, that's basically 0. Okay. That's like how you really want to think about it. Okay. Another kind of, more pedantic way of thinking about it is that, well, I can, I'm going to factor out an x squared out of the top and the bottom. Okay. So I look for the highest power. And then I divide the top by that highest power, and I divide the bottom by that highest power. Right? So I get this 4x plus 3, and I get this x squared plus 3. Right? I divide top and bottom by the highest power that's there. Right? And you see what's going to happen. Right? This is going to be 4 over x plus 3 over x squared. On the bottom, I'm going to get 1 plus 3 over x squared. Right? And as x goes to infinity, well, these guys basically become 0. This becomes 0. We get like 0 over 1. Right? So for x large, this is basically 0. Okay. That's another maybe more proper way of thinking about it, like more algebraically, rather than these 3's don't matter, right? That's sort of more hand wavy way of thinking. But it boils down to the same thing. It boils down to the same thing, right? Right, because what's going to happen, and this kind of gives some teeth to the idea that the 3's don't matter, right? Because as x goes to infinity, these guys are going to vanish much faster than these guys, than this guy, right? 3 over x squared is going to go to 0 much faster than 4 over x. So that's why the 3's don't matter, right? Because they kind of shrink to 0 much faster, right? And so this basically turns into 4 over x over 1, which is what we had over here. Okay, so in any case, right, we were thinking about the, right, so for the horizontal asymptotes, as x goes to positive infinity, this thing becomes 0, right? So r of x tends to 0. And if you go to negative infinity, the same thing happens, right? Because you've got this 4 over x. It's a negative number, but it's still going to tend towards 0. As the bottom becomes huge, this is going to become 0, right? So as x goes to plus or minus infinity, it's gonna be 0, right? So you know that it's got some asymptotes. It has no vertical asymptotes, but you know that as it goes off towards infinity, it tends towards this line y equals 0. Let me have you do one. R of x equals negative 2x squared over x plus 1, x minus 2. Okay. So tell me about the asymptotes. So, what are the asymptotes of this rational function? Okay, turn to a partner and talk with them, please. Okay. Anybody want to tell me where are the horizontal asymptotes? Where are the horizontal asymptotes? Just need to. What do we need to do to check the horizontal asymptotes? Let's do the vertical ones first. So where are the vertical ones? -1 and 2, right? So we see where the denominator is 0, right? X equals -1 and x equals 2, right? You know, if we were in something in a case like this, right? If we had something like this on the top, then that actually wouldn't be a horizontal asymptote. You guys see that? Right? This actually wouldn't be a horizontal asymptote, but because we made that assumption that there were no common factors, we don't have to worry about it. We just have to look for the zeros on the bottom. Right? We don't have to worry about cancellation with zeros on the top. And then the horizontal asymptotes. Anybody figure that out? Those out? That out? What happens as x goes to positive or negative infinity? Stella?
I wasn't really sure exactly, but
Yeah.
the way I was thinking about it maybe was, so, I mean, if you have the bottom right, so infinity plus 1 and infinity minus 2 is just basically going to be infinity squared.
Yes.
Right?
Yes.
And then you have infinity squared on the top times -2, so would it tend to -2 maybe?
Yes, that's exactly what will happen. Yeah. Basically, and that's kind of the right way you want to think. It's like, well, you know, basically this thing on the bottom, we don't have to pay attention to anything here except for the top term, right? And the top term on the bottom is this x times this x, right? There's a square on the bottom. There are some lower order terms, but we don't care about them because we're going to infinity, right? So you think, okay, well, you know, this is, you know, basically -2x squared over x squared, right? And then, you know, -2x squared over x squared is -2. So, right. So, yeah. So this is like as x becomes huge, right? As the size of x becomes huge, well, you know, this thing basically is -2. Yeah, Vicky.
Like what I was thinking about
Yeah.
is including the x's when you like multiply the
Yeah.
two
Yeah.
vertices
Yes.
together.
Yeah.
Which made me think that like the denominator was larger because there was like the x squared and also the additional like.
Yeah, but remember it's the same sort of thinking. So let's multiply it out. So suppose we have those x's in there, right? We've got x squared minus x minus 2 on the bottom, right? Okay. So we can play the algebraic way of thinking and say let's multiply both top and bottom. Let's divide top and bottom by x squared. So on the top we're going to get x squared. On the bottom we're going to get 1. I'm sorry, on the top we get 2, because we divided out the x squared. On the bottom, we divide everything by x squared, and we get 1 minus 1 over x minus 2 over x squared. Right? This is that game we played over there. You know, multiply top and bottom by 1 over the highest power term. Right? And so we get -2 on the top. And here, distributing that factor, we get 1 minus x over x squared, and then -2 over x squared, right? So those x's, I think you're thinking that maybe this x is going to have maybe this x is going to do something, but ultimately it just vanishes. So yeah, so these guys, as x goes to positive or negative infinity, all this stuff goes to 0, and you end up with negative 2. Okay, we didn't get as far as I hoped, so we'll finish up next time with this business of graphing rational functions, using some of these things, and playing the same trick we did last time.